Okay, assume you've read and worked the problem. Let's get going here. I definitely want you to study part B when we get to it. That's a very common question, and it's a very easy question, but it's very confusing the way they state it. So definitely study that one after we go over it. Part A, ratio test. Well, we've done that one quite a few times now. Limit as n goes to infinity. The n plus 1th term will give me, I'm going to leave the oscillating term out of it. I don't really care about it right now. So the n plus 1, so when I plug that in, I'll do a little cleaning up. I actually get 2n plus 3 over, clean up again, 5. So I'm actually plugging in n plus 1, distributing and cleaning up. Just kind of save some time there. Now the nth term, I'm going to go ahead and divide by it, which means multiplying by the reciprocal. Okay, so when I divide, I subtract those powers, so I end up getting x squared, right? 2n plus 3 minus 2n plus 1. Okay, and then I'm going to go ahead and group my n terms together like we always do. When I go to infinity, highest term, then I end up going to 1. So I end up getting absolute value of x. Now remember, or x squared, you have to be less than 1. Okay, now once the interval of convergence. Now remember, x squared can go in both directions. As long as you're less than 1 or greater than negative 1, because it's a square, it's a positive number, you're good. Okay, now this is the question here. The big thing is determining the interconvergence. I would put parentheses negative 1 to 1. Move on to part B and C, because checking whether those are parentheses or brackets takes a long time. It sucks up your time, and it's only worth 1 point. So go to B and C next, and then come back to part A. Okay, but since we already assumed you've worked it, I'm going to go ahead and check whether those parentheses or brackets. So if x equals negative 1, okay, I'm going to go back up here to the original. Let me erase some of that. So I'm going to plug in negative 1 for x. I'll end up getting, oh, why do you scroll back up? End up getting the sum, negative 1 to the 3n plus 1 over 2n plus 3. Now this is an alternating series, okay, and its limit is 0. So it tells me it converges by the alternating series test. I'm not going to get into showing all that work there. Like I said, it's very few points. I just need a justification. Okay, so now same thing. If x equals 1, oh, so since it converges, I know that's a bracket. Same thing, plug in. I'll get negative 1 to the 4th, 2n plus 3. Same thing, that's going to converge by the alternating series test. So since they both converge, I have brackets. But this can be a huge time sucker. So put parentheses and move on and come back to it when you have time. Now part A was worth 5 points. Okay, that's quite a bit. So here's how it breaks down. Set up the ratio test, actually compute the ratio test, find the actual interval, negative 1 to 1, that's another point there, and then B, if you consider both endpoints and then do the analysis, you'll get a total of 2 points there, for both, 1 for each, okay? So 5 points for part A, so that's a big one. Okay, part B is the one I want you to study. It's very wordy and very confusing. It says the Maclaurin series for G evaluate x equals 1/2 is the alternating series whose terms decrease in absolute value to 0. The approximation for G of 1/2 using the first two non-zero terms is 17 over 120. You actually don't really need to know that. Show that this approximation differs from G of 1/2 by less than 1/20 or 1 over 200. Okay. Now, this is the first two terms. Now, by definition, my error bound, okay, is going to be less. So if I take my error, so if I take the real answer, G of 1/2, whatever that may be, and I minus, they tell me it gives me 1/20. You don't have to use this notation. You could also use the notation that the difference between your real and your approximation, right? Because that's what that is. It's an approximation. So I said the polynomial at 1/2. Either one of that notation is fine. But basically between my approximation and the real terms, this is the real, that's my approximation, is always going to be less, and I put absolute values because it's the difference. It doesn't matter if you're over or under approximating. So that takes care of my signs. It's always less than the next term. So this is using two terms. So I need to look at the third one. So it's always going to be less than that x to the 5th over 7. Now x in our case is 1/2. It's a 2. Work that out. That gives me 1 over 224, which is in fact less than 1 over 200. So I just showed that's less than that. So as long as you have that next point. So this is worth only 2 points. So if you recognize you need the third term and then just actually writing it all out as your error bound is another point. Okay, but this is a very, very common question. It's just confusing how they say it. But if they're asking for the error, you always want to look at the next term higher. Okay. Part C, find the first 3 non-zero terms in the general term for G prime. Okay, so this part's not bad. This is worth 2 points. So here's my first 3 terms for G. So G prime is just using the power rule. I get 1/3 minus 3/5 x to the 2nd plus 5/7 x to the 4th. Here's my first 3 terms. Let's do the general term now. Okay, well here's my general, so I'll just take the derivative. Now for stars, I'm just going to leave that -1 to the n as is, and then I'll check my signs when I'm all done. Okay, power rule. So when I bring down that power, I have 2n plus 1, and that's still over 2n plus 3. Oops, I need an n in there. Subtract 1 from the power. Okay, now let's check it. So if I plug in 1, okay, I should get, let's see, lost my place here. Nope, so we're good. We're good. We checked it. You're still oscillating, so that's good. We're fine. Very tricky because it looks like my first term is positive, and that's why I hesitated there for a second. But see how I'm actually going, n is 0, 1 is not there, 2 is here, 3 is not there. So it's kind of tricky there, the way it kind of disguises itself. But we typically do not touch that oscillating part when we're doing a derivative.